morning, dear students. In the last module, we had discussed about the motion of a projectile. The concept in the motion of a projectile was the acceleration due to gravity is a constant acceleration acting on the body which is projected, and the velocity therefore changes in its vertical component while the horizontal component remaining the same. Therefore, the body which is affected by a constant acceleration in a particular direction always is discussed there, which is found to be a parabolic path. So in the case of that, if we take a parabolic path, the velocity is always in that direction, acceleration due to gravity is always downward there. That is velocity, this is acceleration. So in this case what happens is, when the inclination is like this with the obtuse angle between velocity and acceleration, the velocity goes on decreasing. So when it comes to this point, acceleration is still like this. You can see velocity is like that. The angle of obtuse angle is reduced here. Velocity is here, acceleration is here. When it comes to this topmost point, velocity is horizontal, acceleration is vertical, this is 90 degrees there. When it comes to next point here, you will see the velocity along the tangent, acceleration due to gravity downwards. This angle is always acute angle, less than 90 degrees. You can see that. So like that, as it comes down, you will find the angle reducing further. Whereas in every case, the direction of acceleration is the same, constant acceleration. So therefore, as a matter of fact, when the angle between the acceleration and the velocity is obtuse, the velocity goes on decreasing. And as it becomes at right angles, 90 degrees here, then it will be horizontal, velocity will be horizontal, the acceleration is vertical. Further, when the angle becomes smaller, the speed again goes on increasing, the velocity along this direction goes on increasing. So, for the body to move on a curve like this, there is an acceleration vector required, and this acceleration vector will influence the magnitude of velocity as well as direction. But you will see, when the acceleration is perpendicular to the velocity, here this acceleration is not influencing that velocity anyway. Therefore, we have got a parabolic path here. If you have always the acceleration at right angles to the velocity itself, then how will be the motion of the particle? Instead of having obtuse angle here, acute angle here and so on, suppose you have got the same sort of at right angles, the angle between 90 degrees between the velocity and the acceleration there, then how do you find the nature of that curve? Naturally, it will be much more symmetric than this curve, and that is a circle. A circular motion takes place, a smooth curve, and this here has acceleration always at right angles to velocity at every point. So the circular path is described like that, with a constant speed suppose. Then you will find always this velocity, suppose it is moving like this, velocity is always perpendicular to that one. So this acceleration cannot influence the magnitude of the velocity in this direction. Such a case we are going to see here now, which is called the motion on the circle. So we shall see that now. Motion on a circle, that is the present module. Imagine now a body moving on circumference of a circle like this. The velocity is like this. Suppose it is moving from here to that point. This is point P1, this is point P2. Between these 2 points that is the displacement P1, P2 along the straight line, and the velocity here is along the tangent like that. The velocity here is along the tangent like that. Suppose the center of circle is somewhere here. So this is the radius. This is the radius here. Radius of the circle. This is the displacement here. I call it as some delta S. This is the velocity here. This is the velocity here. Let us consider a case as this, where the body is moving with the velocity at P1 with the velocity V1 along the tangent. At V2 the velocity is V2. At P2 the velocity is V2. It is moving, the radius of the circle is this, and this is the center of the circle O. If a body has to move like this on the circumference of the circle, the position of the body should be changing continuously on the circle. That means the velocity direction must be continuously changing. Then only it can take a curvilinear path. If the direction of velocity does not change, it has to go along a straight line only. So if you now make the body just leave it at this point to go in its own way, it will go like that only, tangentially. So as a matter of fact, therefore, this change in direction of velocity requires an acceleration. We have said that acceleration is a vector quantity. This acceleration will have two components, parallel component, perpendicular component. Acceleration vector we call it. Acceleration is a vector. Two components are there for that. One parallel to the velocity, that is along tangent, and that is perpendicular to the velocity, that is along the radius. That will be the case. Let us see how this acceleration is to be analyzed now. Then we will know what the influence of that will be. Let us say this angle is some delta phi, some small angle there. If you want to know the acceleration, you must know the change in velocity. So let us draw the vector here separately. Suppose V1 is equal to V2 in magnitude. Well, directions are different, suppose. That means the body is moving with constant speed along circumference of a circle. Such a thing is what is known as uniform circular motion. Uniform circular motion means it is having a constant speed on the path. Direction must be changing, of course, because it should be on the circular path. In this case, if you represent the velocities V1 and V2 on a vector diagram, drawing a line parallel to this one, that is V1, and drawing a line parallel to that one, this is V2, and you know both are equal, and the angle between this and that is nothing but delta phi, because this change is coming because of that angle only. When P2 is at P1, that means this point is here, this is the radius. When it goes from P1 to P2, radius is shifting to an angle theta, delta phi. That's why the angle between the velocity vectors also will be equal to delta phi. Now if you take complete the triangle here, this will be the delta V, that is the change in velocity. So change in velocity will be in that direction. You can now see change in velocity is perpendicular to the velocity here. This is acceleration vector. Change in velocity will be in the same direction as that, because A is equal to, acceleration vector is equal to dV by dt. That means delta V by delta t. When in the limit when delta t becomes 0, we call it as dV by dt. That's all the difference. So delta V by delta t, initially we can write like this. Suppose time taken from here to go there is delta V. So if you want to know the relation between these things, you want to know the velocity and acceleration coming responsible there, let us find out the relation here. take these two triangles. One is the velocity triangle and that is the acceleration triangle, the position triangle here. So these two radii are equal, like these two velocities also are equal in magnitude. So length of these lines are equal, like length of these lines are equal. There is an angle between them, same angle here. So two sides are equal and angle between them is same. That means these two triangles must be similar. So what we can see from this is the relation. We can find out this delta S by R, the ratio must be equal to delta V by V here. You may call it as V1 or V2. We may say V1, or we can also call it as delta V by del V2 also you can call it. Either way you can put it. Because in magnitude this length of the line is delta V. V1 or V2 both are equal because V1, V2 are equal. V1. So to put it very simple, we can call it as delta S by delta S by R is equal to delta V by V. We can call it like that. Therefore, delta V is equal to V into delta S by R. Now when the body is moving or particle is moving on circumference of circle, from point to point what is changing is the position. P2, P1, P3 like it goes on changing. Accordingly, the displacement is changing. That delta S is changing. Whereas the speed along the curve is the same. That means V is constant, R also is constant. Radius is constant. So what is changing is this one. Now you want to get acceleration according to the definition. The acceleration responsible for this movement is A, that is delta V by delta T. We are talking about the magnitude of this one. Initially, let's take up the magnitude there here. Delta V by delta T. If you want it in vector direction, directly you have to put these two also. Delta V by delta T. So you apply this equation accordingly. You will find this is V by R into delta S by delta T. Again here delta S is the displacement from P1 to P2 like that. Goes on like that. Now you can see this is the case, the acceleration when it goes from P1 to P2. Change in velocity when it is going from P1 to P2 in this change. If P1 is very close to P1, that is in the limit when delta T tending is 0, you will find this delta S by delta T is equal to ds by dt, we call it. The ds by dt is nothing but the velocity, change in velocity. That ds by dt, the ds by dt is velocity here again. So in the limit of this we can write this v for that also. So if write in magnitudes now, we can write A is equal to V into V by R, writing only magnitudes now. For this we write V. Direction we will see what it is next. So V by V, so V into V is V square, that's by R. So that is the acceleration, V squared by R. This is magnitude of the acceleration. What will be the direction? As I told, direction will be along the direction of change in velocity, the direction of the acceleration. So change in the velocity direction, this is not the displacement, this is the velocity direction here, whereas this is the change in velocity taking place like this, you can see. So change in velocity in the limit when P1 is very close to P2, the delta V will be along the radius itself in that direction. So that will be direction of acceleration. That acceleration is perpendicular to the velocity now. Because the speed of it is not changing, there is no component of acceleration taking place along the tangent there. So it must be only along the radius. So that acceleration is what is known as radial acceleration, we call it. Radial acceleration, we call it. Therefore, we write like that, A radial. So this is what is V squared by R. It is going with uniform circular motion like this. This is the situation. There is no component of acceleration along the tangent. All the acceleration is along the radius, and that is called radial acceleration. Sometimes it is also known as normal acceleration also. Normal because it is perpendicular to the velocity. So unless there is a perpendicular component like that, this will not take place. This velocity, this equation of acceleration can also be represented in terms of time period. Now that it is traveling with uniform speed throughout, the time taken for every revolution will be the same. So the speed is given by, that is v, the speed is given by 2 pi r by t. What is this t? Where t is time period of revolution, time taken for one complete rotation, like around that. So that is t. So therefore you can write v in terms of this also. If you substitute like that, radial acceleration can also be given by 4 pi r square by t square. So this is how we can put there, and this is v square by r is there again, so one more r comes, so the equation will be 4 pi r by t square. So that is the radial acceleration. This acceleration is always toward the central circle, so it is also known as centripetal acceleration. Centripetal acceleration we call it. You will find that at every point, when the body is at this point, there is an acceleration dragging that way, and therefore it is changing direction every time. So everywhere the same story goes, everywhere the same story. It will be like that. That is radial acceleration. That is the case of uniform circular motion. Right? So if it is not uniform circular motion, then how it will be? That means, suppose the speed of it also is increasing continuously. Then what is to be known? We shall see that. In the case of non-uniform circular motion, the speed is not constant. That means v1 is not equal to v2. Either v1 is greater than v2 or v2 is greater than v1. Something should be there in magnitude. Let us see how it will be. Let us say a body is moving on the circumference of a circular path like this, which is non-uniform circular motion now. That means I told you velocity at both points is not the same in magnitude also. That means the velocity at this point, if it is v1, the velocity at this point, say, is v2, both are not equal in magnitude. Then what will be the case? Suppose the acceleration is somewhere, it is like this. I draw here the picture, v2, v1 here. I have just put the vector figure here for you to understand. This is v2, this is v1, this is delta v, that is the acceleration direction. So v2 is greater than v1. You can see in the picture the length of the line is more. So in this case, that means the speed is increasing as it is going like that. Then what will be the direction of the acceleration? It is like that. It is going in that direction. That means if you now have two components for this, one parallel to the velocity, that is towards radial, one here, that is one here. Parallel to velocity means in the direction of velocity itself. I write here. I repeat. Suppose the velocity v1 is in this direction given in the vector diagram. For clarity I have to separate the figure here. v2 is in this direction. Suppose v2 is more than v1. That means the body is speeding up while going around circumference. Magnitude also is increasing. Length of the lines are not same. v2 is greater than v1. This is the case what we are talking about. Then the acceleration is along the tangent, along the change in velocity, that is delta v. This is the acceleration vector. This can be now resolved in two components. A parallel and A perpendicular. This is what is called the radial one. We can see this is the one which is along the direction of the velocity, parallel to the velocity direction. So that is responsible for the increase in the speed of the particle on circumference. Whereas this component A perpendicular is the component which is acting in this direction. That is the radial direction. So that is one which is acting perpendicular to the velocity. So that is one which is taking radially. That is the central the acceleration that is responsible for the change in the direction of the particle there. Velocity direction is changed by this one, magnitude is changed by that one. So that is the difference what we have in the case of non-uniform acceleration. So change in velocity is given by this component in magnitude. Therefore, we try to get the value of the v square by r for that only, at that point only. So at that point, this normal component is given by v square by r. Whatever is the velocity here, v by square by r. That is what is happening. If it goes next point, it goes to another velocity. Velocity is different there. v2 square by r there. That is radial component here. So radial component at every point will be changing in magnitude there. Direction will be always toward the center there. So that's what you will understand in the non-uniform acceleration case. You can now see the various positions where the velocity and acceleration will be there on a circumference of a circle here. If you see in this case, the body is moving on circumference of a circle like this in a vertical way, like this. Suppose in this its acceleration is increasing. That means the acceleration is trying to create more velocity. Speed is increasing. So that means the parallel component is like this of the acceleration. Radial component is like this. Radial component is the same everywhere. That means it is always directed towards the center only. Parallel component only is changing direction. Accordingly, the acceleration also will change. The direction of the acceleration will change. Magnitude also will change because the speed is not constant. If the speed is constant, the magnitude of the acceleration will be constant, and the direction will be always towards the radial there, radial direction there. So you will see here, it is inclined like this. You can see here, it is inclined like this, and here it is like this. This is the acceleration. That is the parallel component, is radial component. When it comes here, this is the acceleration radial, parallel component, and that is the acceleration direction. Similarly here, acceleration is here. This is having two components. One is parallel and is perpendicular like this. So at every point you can identify the direction of acceleration as well as the velocity there. Only thing that you must remember is a radial acceleration is a must if it is moving on circumference of a circle. It is required there for changing the direction of the accelerated velocity from point to point, and that is given by v squared by r, where v is the velocity at that point. As it moves now in the uniform circular motion, therefore it will go on with the uniform speed all along the path, and direction is always along the tangent there. Because direction is changing, there is change in the velocity, and therefore that is given by the acceleration here. That's what you understand. In the case of non-uniform circular motion, speed also changes. Parallel component also will change for the acceleration now. In the earlier case, parallel component was 0. Here, in the case of the non-uniform acceleration, parallel component is not equal to 0. That is to be remembered. So based on that, we can now think of the problems on this. We have discussed the case where the body is speeding up while going on circumference of circle. Suppose it is slowing down on going circumference of circle now. Non-uniform acceleration once again, non-uniform velocity again, but the case of decreasing speed. So, for example, then what will be the case? Suppose the body is at this point now, the velocity is in the direction, the normal radial acceleration must be there, and because the speed is going to change when it goes from here to there, this is V1, this V2 at this point, and this V2 is going to be less than V1, it is getting reduced there. So there must be a component of acceleration which is parallel to the velocity but retarding this velocity, this speed. So a parallel component will be in this direction now. A parallel component will be in this direction. This is what we call as radial acceleration. Sometimes this A perpendicular, as we say, A radial acceleration we call it, and A parallel is known as A tangential as also. This is along tangent. So this is the tangent. So along this is the component. This is the vertical component for that. That is the normal component for that. So therefore resultant acceleration will be in this direction. That will be the acceleration. As it comes here now, say for example, this is normal component in this direction, and it will be in this direction. Acceleration. This will be retardation here. A parallel component, tangential component. This is a normal component, perpendicular component. This is the acceleration now. So the direction of acceleration, as you can see, it is going on changing, and that is how the radial acceleration is to be understood now. So when it is going on the circumference of a circle like this, depending upon the it is speeding up or speeding down, the component of the parallel acceleration will change. Wherever the speed is maximum, then the tangential component or the radial parallel component will be maximum. Wherever the speed is minimum, then the normal component will be maximum there in that direction there. So we can see that in the particular circular motion. So for example, a roller coaster you are trying, see for example you are going around a roller coaster, you understand that. At the bottom of that, it will have maximum speed here. So here the parallel component will be there, and that acceleration is maximum here. So this normal acceleration will be in this direction. So we will find maximum acceleration here. Acceleration is maximum here. As it goes up, here it slows down. So here the speed becomes minimum, and therefore here the speed is minimum. His speed also is minimum, maximum here. Therefore A parallel component is maximum here. Here A parallel component is minimum here. A normal component is perpendicular component here also, here also. So like this you will get two different varying accelerations as it is inclined like this. Suppose it is on this side now, it is increasing speed, now it is coming down from there. As it is going up, it is slowing down, like what I have shown in the figures here. The acceleration parallel component will be having a retarding effect on that. So when it is coming down from here, suppose in this direction, the velocity in this direction, the normal component of acceleration like this, the parallel component is here increasing, so you will find acceleration, net acceleration in this direction. This is perpendicular component, this is parallel component. You will find therefore it is inclined here. So if the angle between the velocity and the acceleration is acute here, you will find it is increasing velocity. Angle between the velocity and this is obtuse here, you will find decreasing velocity, decreasing speed. So that's what you will find in the case of a roller coaster example. We can take numerical problems given like that. For example, we give you, suppose it is said in one case, let us say the velocity at the bottom is 3 times the velocity at the top, say it is given, and you have to find out the that means the ratio of the velocities are given by v bottom by vt, that is 3. So that is what will be the case there. Accelerations now. Acceleration at the bottom to acceleration at the top you want to find out, say the ratio. This is v bottom square by r. This is v top square by r. That means you will find this is vb by vt, that is 3 square, r gets cancelled, so it is 9. So acceleration at the bottom is equal to 9 times the acceleration at the top. You can get the relation between this here to there, the acceleration relation. Net acceleration, I mean, this means net acceleration. So like that, the value of the accelerations at any given time, and hence the radial and the tangential accelerations can be calculated. You can work out the numerical examples given in your book now. Thank you.